Then our next speaker is Debashish Mukherji, or sorry for the. So he comes from Max Planck Institute for Polymer Research Mines in Germany, and is going to tell us about soft, smart, multi-responsive materials under alcoholic intoxication. So we're looking forward to that.
Okay, thank you for the introduction. So here's the title of my talk. So I'm from the Max Planck Institute for Polymer Research in the theory group of Kurt Kramer. So basically, this is the title, and why I must start with this thing called why soft matter soft, because this is important here. So what we have here is our relevant energy scale is of the order of thermal energy, which is kT, and therefore properties of polymers are extremely dictated by large conformational and compositional fluctuation. So this is what we want to understand in the soft matters, and this last part that I write, complex matter, where simplicity matters, because these are usually very complex macromolecular systems, and I hope I convince you at the end that these could be understood by very simple, let's say, physical concepts, and we do not really need to understand it from very, very detailed chemistry, so to speak. But before I proceed, I should already start by acknowledging my collaborators. So I started this project with Professor Kramer at the MPIP, and Carlos, who was there for sabbatical, so he did a lot of work with this theory of our system, bunch of PhD students, visitors, collaborators. These are all the co-authors, and of course many other people who are not really co-authors, but I discussed a lot with them. So I start with this polymer phase diagram. So in broadly speaking, we can distinguish it between two categories. One is upper critical solution temperature. So when we have a system which is collapsed, we increase the temperature, this guy opens up, and this is an energy driven process. On the other hand, the more interesting one is this LCST. So LCST is at low temperatures, the polymer will be solvable because there are some subtle interaction kicks in. But when we increase the temperature, the solvent monomer interaction goes down, and solvent particles get expelled out of this polymer backbone, thus gaining translational entropy, and the polymer collapses because of this translational entropy, which is larger than the conformational entropy loss upon collapse. And one of the classic examples of this smart polymer is polyisopropyl acrylamide, which is basically, this is a typical chemical structure of a monomer where it has a hydrophobic backbone, and this isopropyl, no, not isopropyl, this is amide, hydrophilic amide group, and then the isopropyl hydrophobic capping, and this guy in the middle forms hydrogen bond, and if you increase the temperature, this hydrogen bond breaks down, and thus the polymer goes from coil to globule transition. This polymer is interesting because it has a transition temperature around 305 Kelvin, which is our body temperature, makes it very useful, but can we tune it? So this is just an example that if we now take a polymer of polyisopropyl acrylamide, and then we can copolymerize it with something which is more hydrophilic, so to speak, let's say, just as an example. And this is this polyacrylamide, and this is a plot where we show that mole fraction of acrylamide monomers along the backbone of a polymer, and how does the transition temperature changes. Of course, we do not exactly, simulation doesn't exactly reproduce experiment, but we get the correct trend, and this is not really surprising. But the problem here is that, can we have a predictive behavior? Here it's not, because if we know what happens at 5%, we cannot predict what will happen when we put 50% of acrylamide, because it is non-linear. So can we have something which is more predictive? And the answer came from Jeffrey Kopperstein group in Columbia University. So what he did is he synthesized this polymer together with a couple of his PhD students. And what he did is, this polymer have very simple, let's say, monomer unit, which is ethylene oxide, which is here, and the methylene. And what he does is he only, so methylene is of course hydrophobic, ethylene oxide is water soluble polymer, and what he does is he changes the fraction of these two guys. So if we now keep hydrophobic part fixed and linearly and increase the number of units of hydrophilic part, the transition temperature or cloud point, because they look for higher concentration, it linearly goes up or other way it goes down. And that makes it a molecular toolbox, because we can basically, we do not really need to do experiment for every single composition, but this can be a guiding principle what we need. But the problem is nothing comes for free. And if we now take one of these polymers and we calculate, for example, chain length effect, so where we have ended termination with either hydrophilic or hydrophobic termination, what happens is, in order to get this converged cloud point temperature or transition temperature, we need something of the order of 10,000 grams per mole. And this, just to give this thing in perspective, if you have a pure ethylene oxide, this will be something 220 monomers in a chain, roughly. Now the problem is, anybody who does simulation, they know that this is almost impossible to do with this long chain, with all atom details. So we have to come up with a different solution, and the solution is we do coarse graining. And because we have a linear behavior, it simply means the two units are decoupled from each other. So if we increase one unit, it doesn't affect or it doesn't disturb the effect because of other units. So it makes it a, that's why we could do a segment based coarse graining. So we put a bunch of monomer in water and calculate cross interactions, and this is basically two different composition or this ethylene oxide and methylene composition that you can see, and we have like this one-to-one mapping that we do here. We have one set of coarse grain parameter between different unit. Of course, it is at state point dependent, so we did it for one temperature, and then this is basically a nice comparison between experiments that we know from Jeffrey Kuperstein, and this is for different units, and then these are basically turbid because, and we did always this 10,000 grams per mole, but a single chain in solution, and then we get like almost all the numbers correct except these two things, yeah. So which is reasonably reasonably good. That's what we think. Now the thing is, it is all fine that what we do in pure water, but in some cases, again, polyacrylamide, if we put it in aqueous alcohol mixture, what happens is this LCST, if we start from pure water, which is 0, and pure alcohol will be 1, if we start with like this 32 degrees C or 305 Kelvin, by adding alcohol, what happens, LCST goes down. And this is the work from Francois Winnick and Matt Tyrrell long time ago. And now if we take one temperature, so to speak, something here, 20 degrees, and then we just keep the temperature fixed, and then we increase the concentration of alcohol, what happens is polymer goes from coil to globule transition and back to coil again. And this is what they call, so pure water is good solvent, pure alcohol is good solvent, in between polymer collapses. And this is what, say, they call it less co-non-solvency. And this is what we want, one of the things that we want to understand. So we have two individually good solvents for polymer. Both solvents are miscible, because if you know from floryhuggins theory, if it was immiscible, it would be very easy to understand. And intermediate mixing ratios, polymer collapses, and we don't want to understand this phenomena. But as it turned out that, okay, in physical chemistry, people talk a lot about polynipalm, but there are a lot of systems that also show co-non-solvency. And apparently this term, co-non-solvency, came from this 1978 work of Barndolf, where he did it for polystyrene in cyclohexane and DMF. That's where this name was coined, co-non-solvency. So there are two solvents, and there are a bunch of polymers. So can we, because we have a broad range of polymers showing this behavior, can we put it in under a generic concept, so that we do not care about chemistry, but we only care about, let's say, like relative interaction between polymer and solvent and polymer and co-solvent, yeah? And this is what we did. So we start with the all atom simulation, and then we map it onto this generic bead spring model, where these monomers are just connected by spring. And then we tune the interaction between red and green with the monomer in a way that we produce certain property of interest from all atom simulation. And this is just an example where we have experiments. So we have all atom simulation. So basically we did a simulation of 100 persistence length chain, which is 256 monomers long. We did all atom simulation. We did generic simulation that I showed before. And of course, we have also analytical theory that Carlos did. But experiments are slightly lower, because when Mark Watson synthesized this polymer, he only could synthesize up to 83 persistence length. So that's why it is a little bit lower. But agreement seemed to be rather convincing. But the question is that we reproduce experiments, but this is not the goal of simulation because we want to understand and give insight into the system. So what is going on? So if we have two solvents and we have a polymer, and both solvent like our polymer equally, nothing should happen, polymer should remain expanded. Only when we put this asymmetry, that polymer solvent and polymer co-solvent, they have asymmetry in their interaction. In this case, it is of the order of 4 kT per monomer. Then only we see this size coil to globule and back to coil transition. But then again, this is our hypothesis at this point. So we went back to all atom simulation again. And this is basically what it says is if we have a polymer which is sitting, the backbone of the polymer is sitting at 0, and as we go radially outside the polymer from the polymer backbone, we look into what is the concentration of alcohol in different solvation shell. And one means it is basically exactly what we started with, let's say like 10% alcohol in 90% water. And what it says is basically alcohol is preferred in the first solvation shell. So preferential binding of alcohol with the polymer. But then again, it is like in an all atom simulation, we know that it is as good as the force field. Can we do a little bit more? So Manfred Wagner in our institute, what he did is he came up with this idea. So he made an NMR tube like this. He put it in 2 compartments. On the top, he has this lot of polymers with solvent, co-solvent. I think it's 20% alcohol and 80% water. Below, he put 20% alcohol and 80% water. And what he does is he monitors it over for 16 days. And what he sees is, and it is airtight, and in this filter in the middle can let the solvent go up and down, but no polymer can go down in this bulk region. And it's airtight, so there is no evaporation, so to speak, as you can see from this plateau here. And we see that in like 3-4 days, there is basically 3% decrease in alcohol concentration here, an increase of alcohol concentration, so the alcohol is getting sucked into the polymer. And this idea also works for a system of polynipam in aqueous alcohol again. And what it shows is that we know polynipam is a LCST polymer, but under certain concentration of alcohol, which is like this, let's say 50% or so, when you increase the temperature, polymer first collapses and then it starts to open up again. And this increase, this UCST-like swelling is not really UCST swelling, or it is not driven by energy, but what is happening is if we take like 50 degree, 330 Kelvin or so, water is poor solvent for polynipam, and nothing like this is known from alcohol. So what we are doing is we are just mixing good solvent in a poor solvent. So slowly polymer will open up, and that is this plot. So basically this is for this 330 Kelvin. Now, like I said that we want to see some insight, so we also did some thermodynamic analysis. And what this is a plot where we have a chemical potential per monomer as a function of alcohol concentration. And as we see for different, okay, of course it is a master curve because we properly normalize our system. As we increase alcohol concentration, chemical potential keep going down and down and down. And it simply means by addition of alcohol, solvent quality is becoming better and better and better, which is surprising because if we know from floryhuggins theory, and if your polymer is collapsed, it would be energetically more unfavorable to solvate it. So what should happen is you should have this low, and then chemical potential should go up, and then it goes down again. And this is what floryhuggins should tell us, but this is not what we see. And this brings me to one conclusion here, which is a bit surprising to us when we saw it first time, that we have a solvent which is water, alcohol, and alcohol. Polymer is expanded, collapsed, and expanded, but the solvent quality is getting better and better and better. And it simply means that polymer conformation is decoupled from solvent quality, and polymer is collapsing in good solvent, which is a bit counterintuitive. But then, of course, it's not, we see this behavior, but can we also do some theory for that? And the easiest way that one can do is this floryhuggins theory. So if we write down in floryhuggins free energy, and then we get the second order expansion, we get this excluded volume, monomer excluded volume. And then we get this term, which is polymer solvent, polymer co-solvent, chi parameter, and solvent co-solvent. And what happens is if solvent co-solvent chi parameter is 0, then there is nothing should happen. only when solvent co-solvent parameter is less than 0, we should see this coil-globule coil transition. And this is, and it is known from standard Conon solvency solvent co-solvent mixtures like aqueous alcohol, this chi parameter is very close to 0. So this is just a simple way to explain this thing that, okay, this is why floryhuggins fails to explain this phenomena. But can we do a little bit more? So this is what Carlos did this theory. So what he did is he said that, okay, let's assume the polymer as an adsorbing surface where alcohol and water, they compete to get adsorbed on the surface. And what we have is, because when you have a very little amount of co-solvents or alcohol, they can bind two monomers which are far along the backbone, forming this kind of solvent bridges. And then we have this kind of loops that has a lot of solvents or water molecules. So that's why these guys are behaving like a good solvent. And what one can do is one can calculate this fraction of bridging, which is here. By simulation you can calculate. We can also calculate it from radius of gyration. And the theory is basically Langmuir light adsorption theory. And from that one can get the equation for chi b as a function of xc. And this basically explains this phenomena reasonably well. And this is what we feel that is the picture behind this Conon solvency phenomena. So what is happening is we have this polymer collapse transition, and of course, as I said, that you have this bridging, and just a poor physicist picture here that we have, like, we think that this kind of interaction is one of the scenarios. This is one of the interactions that can happen, and if this is true, then what will happen? The side chain dynamics should be, let's say, reduced, or side chains will be rather rigid. And this is again, let's go back to NMR again. And Manfred Wagner, he did this proton NMR experiment, and he looked into dynamics of these hydrogen atoms. And this is basically increasing alcohol concentration. What we see, as expected, this signal goes down and goes up. So it basically here, signal is also going down as well as broader. So the T2 time is basically going down. So the side chains are becoming more rigid as you increase concentration of alcohol in this region, yeah? So this seems like a more or less the complete picture that we saw for Conon solvency. But the problem is, if we look into standard poor solvent collapse, what we have, our collapse in Conon solvency is preferential binding driven. But standard poor solvent collapse is depletion effect driven. It simply means if we have a solvent, let's say black guys, and monomers are these blue ones. So monomer solvent interaction, repulsive interaction should be larger than the repulsion between monomer, and that's where this depletion effects kicks in. And this is basically a typical example will be PMMA in water as well as PMMA in short alcohols. And this is just from a generic simulation, this is structure factor of PMMA in water, and as we can see that this is basically collapsed object, where it is given by this q to the power minus 4 power law. I mean sphere scattering that we know. But the surprising part is that if we have PMMA in mixed solvents, what happens is pure water, here is 0, is poor solvent for PMMA. Pure alcohol, which is 1, is poor solvent for PMMA, but in between PMMA opens up. So this is basically swelling in poor solvent. The previous one was collapse in good solvent, and here it is swelling in poor solvent. So what we did is we did this generic simulation. Of course, we mapped like what we did before. And this is basically a simulation result where we see that just by increasing the asymmetry in interaction, one can have more and more and more swelling of the chain. But the reason behind it, because this is dictated by depletion interactions, in between the concentration, depletion interactions should be depleted, means it should go down. That's what it is. And as we know from experiment as well as from all atom simulation, what happens is, this is for methanol, ethanol. So if we increase the concentration of alcohol and we monitor the total number density of solvents, total number density, it is not really linear behavior, rather it has this kind of dip, which is maximal dip is around 50-50, and this is because there is this CH group of ethanol and methanol. They have this repulsive interaction with water molecules where the OH forms hydrogen bond. And this as it turned out, this dip around 50-50 is what is dictating why this subtle effect is why this guy actually opens up. So in short, so we have depletion forces that are reduced because of this reduced density, because the depletion forces are directly related to number density. This is a second order effect, what we call depleted depletion. And polymer swelling is, of course, is because of this second order effect that we know from colloidal science as well. So this brings me to my conclusion slide. So I basically gave example of two different systems. One is co-non-solvency. I hope that I showed that this is basically a more or less generic phenomena, which is many different systems can show this behavior, and standard floryhuggins is not good enough to explain this phenomena. And polymer conformation is completely decoupled from polymer conformation, and conformation is completely different, decoupled from solvent quality. And what we see, this initial collapse is basically energy driven because of the sticky contacts, which is roughly 4 kT more. So monomer per monomer interaction for alcohol is around 4 kT more than pure water. And subsequent expansion is, of course, entropic driven. And co-solvency, so to speak, the swelling in poor solvent is basically a double depletion effect or second order effect, which only originate at constant pressure, which can be explained by constant pressure floryhuggins that I didn't have time to explain today. And with that, I think I should. That's my last slide.
Thank you very much, Debashish. Questions? On there?
Hi, thank you for the interesting talk. I have a question. Have you tried this alcohol intoxication effect? Have you found this effect in other LCST systems?
Actually, yes. There are these polymers that are in the list here.
What about natural LCST systems such as tropoelastin and other protein systems in nature? Do you think the same effect?
Are you talking about elastin-based peptides?
Yes.
Okay. Yes. Okay. So elastin-based peptides, of course, have LCST, but I don't know. At least I don't know any experiment where they look into this kind of co-non-solvency. But I know one thing that one can do with urea, because urea has preferential binding with your peptides. And then if you just look into up to 8 molar concentration or so, what will happen is instead of, let's say, denaturating your thing, it will collapse it. So if you start with, if you are below LCST and you start with an expanded chain and you start putting it urea, it goes down.
Do you think it's the same principle between urea and alcohol intoxication?
Okay, I must say that intuitively I would like to say so. But I have never done any simulation with urea. So I cannot say for sure that exactly microscopic origin. But intuitively, that's what I think.
Thank you.
Yes.
Yeah, I have the question. Then you talk about the quality of the solvent and so on. It had been very nice to see the second viral coefficient.
Yes, actually, I think, if I remember correctly, like there was a discussion before with some experimentalists from Aachen, actually Walter Richtering, and we were asking him if he can look into his experiments, calculate this quantity. But in simulation, for this case, I didn't calculate it, no.
I was more thinking about the experimental.
Yes, yes.
Because we say that the second viral coefficient would be 0 at the theta,
and I'm negative for, yes.
And positive.
Yes.
So that would give us a little bit better hint.
Yes, yes. So actually we asked Walter Richtering, but that was like some time ago.
Hi, very impressive. You mentioned solution, and I was wondering if the idea works for dispersions. Imagine, I don't know, a nanoparticle decorated with the PMMA chains.
Yeah.
And do you think that we can have this co-solvency effect in that case, or it's related to the macromolecular nature of
no, because
of the molecules.
No, because this depletion effect, this is basically, this is known from colloidal science.
Yeah, but it's bigger in that
yes,
case.
Yes, so there is this work from Arjun Yodh and all these people where they say that the asymmetry in sizes that you need is of the order of 10. So that I know, but this is basically, this monomers, what we have here is rather small.
Yeah.
So to be more precise, how do I say, I mean, I don't know, because if nanoparticles, if you graft it with
PMMA chains, like in your experiment.
Yeah, so ideally I would say probably yes. But
we'll try, okay.
Yeah. But this is a well-known phenomenon, so there are experiments on this PMMA, so to speak. I mean, yeah.
Yep, one last question.
This is not question, this is a comment.
Yes.
If I understand right from your set of results, that there is a change of ratio of both solvent, and it means that there is a change of dielectric constant. And it seems for me that there is a change in conformation of your polymer, and therefore there is change conformation from one conformation to another, and therefore there is precipitation or decrease of radius of gyration, and then there is, after change of conformation to another kind, there is an increase in solubility. This is only common, but it seems to me that it's rather
this is uncharged.
Sorry?
This polymer is uncharged.
It doesn't matter.
Yeah?
Of course.
This I don't know.
Polyethylene glycol is, of course.
Okay.
Yes, I think from your data it follows follows that there is a change of conformation.
Yes.
Yes, only, and therefore it explains. What you did not show, intoxication.
No, okay.
It's impossible to use, of course, for intoxication.
No. Oh well. Yeah, intoxication, I came up with this terminology because it has unpredictable behavior. You know, you never know how it behaves.
Attention, yes, I understand.
Because sometimes it opens up, sometimes it collapses, sometimes it shows UCST-like swelling. So that's why intoxication comes in. I also had another term called drunken polymer, but then I changed it. I used it for something else for DPG. So I thought I should not use the same term all the time.
Okay. All right.
Thank you. Very, very interesting, really.
Thank you.
So let's thank Debashish again.